Imagine a time before time as we know it. Before stars, before planets, before you and me. Go back. All the way back. To the very beginning. About 13.8 billion years ago, our entire universe was smaller than a single atom. Then, in a flash of unimaginable energy, it burst forth. We call this the Big Bang. It wasn't an explosion in space, it was the explosion of space itself. In those first moments, the universe was a searingly hot, dense soup of fundamental particles. It was a chaotic, formless fog, expanding and cooling with every passing microsecond. There was nothing to see, just a brilliant, uniform glow. As the universe expanded, it cooled down. Think of steam condensing into water. The same thing happened on a cosmic scale. The raw energy from the Big Bang began to congeal into matter. Protons, neutrons, and electrons, the building blocks of everything, popped into existence. For the first few minutes, the entire cosmos was a nuclear furnace. It was hot enough and dense enough to fuse protons and neutrons together, forging the very first atomic nuclei. The universe cooked up a simple recipe, mostly hydrogen, with a generous helping of helium, and just a tiny pinch of lithium. These were the only elements around. The ingredients for every star, planet, and galaxy were now set. For the next 380,000 years, the universe remained a foggy place. The cosmos was still so hot that electrons couldn't settle down with atomic nuclei to form stable atoms. They zipped around freely, scattering light in every direction. If you were somehow there, you wouldn't be able to see more than a few feet in front of you. But the universe kept expanding, and it kept cooling. Eventually, it reached a tipping point. The temperature dropped enough for electrons to be captured by the hydrogen and helium nuclei. Suddenly, the fog cleared. Light could now travel freely across the vastness of space for the first time. The universe became transparent. This moment left behind an echo, a faint afterglow that we can still detect today. It's called the cosmic microwave background radiation. It's the oldest light in the universe, a baby picture of the cosmos when it was just a toddler. This ancient light isn't perfectly uniform, though. It has tiny, almost imperceptible temperature fluctuations. Some spots are 100,000th of a degree warmer, and some are 100,000th of a degree cooler. These tiny ripples, these minuscule imperfections in the fabric of the early universe, were the seeds of everything to come. They were the starting points for the grand cosmic story of structure. The universe was now filled with vast clouds of hydrogen and helium gas, but it was almost perfectly smooth. So how did we get from that smooth, quiet state to the lumpy, star-filled cosmos we see today? The answer lies with something we can't see, touch, or detect directly. Something mysterious and invisible that makes up about 85% of all the matter in the universe. We call it dark matter. It doesn't shine or reflect light, but it has gravity. And gravity is the master builder of the cosmos. It's the force that pulls things together, patiently and relentlessly, over billions of years. Those tiny, warmer spots in the early universe were just a little bit denser than the areas around them. They had slightly more stuff packed into them. This meant they also had slightly more gravity. This extra gravitational pull began to act on the surrounding matter, including the invisible dark matter. Like a snowball rolling downhill, these denser regions started to gather more and more material. The rich got richer. The process was incredibly slow at first, a cosmic whisper of attraction. But over millions of years, the whisper grew into a steady pull, drawing in vast quantities of dark matter from all directions. These gathering clouds of dark matter formed what we call dark matter halos. Think of them as invisible scaffolding, or giant spherical skeletons waiting to be fleshed out. They were the gravitational anchors for everything that would follow. The ordinary matter, the hydrogen and helium gas that we can see, was also pulled in by the gravity of these halos. It flowed through the cosmos like water finding the lowest ground, streaming along invisible filaments and collecting in the deepest gravitational wells created by the dark matter. The universe was beginning to form a structure, a vast, interconnected network we call the cosmic web. Without dark matter, this process would have taken much, much longer. The gravity of ordinary matter alone wasn't strong enough to overcome the universe's expansion quickly. The tiny density fluctuations would have been smoothed out before they had a chance to grow. Dark matter gave the process a crucial head start. It was the silent, unseen partner that laid the foundation. It built the cosmic cities before the lights were ever turned on. It was the invisible architect, patiently drawing the blueprints for the magnificent galaxies that would one day populate the universe. Inside these massive dark matter halos, something spectacular was about to happen. The hydrogen and helium gas that had been pulled in was becoming more and more compressed. As the gas particles were squeezed together, they bumped into each other, losing energy and cooling down. Gravity continued its relentless work, pulling the gas ever inward, toward the very center of the halo. The core of the gas cloud grew denser and hotter. This was the crucible where the first stars would be born. A new era was dawning in the universe, an era of light. After about 100 million years of darkness, the pressure and temperature at the heart of these collapsing gas clouds became extreme. They reached a critical point, about 10 million degrees Celsius. At this temperature, a powerful process ignited nuclear fusion. Hydrogen atoms, the most abundant element in the universe, began to fuse together to create helium. This reaction released a tremendous amount of energy in the form of light and heat. A star was born. The first stars were not like our sun. They were giants, hundreds of times more massive and millions of times brighter. They were brilliant, blue, and lived very short, very violent lives. The light from these first stars blazed out into the dark, neutral universe. This powerful radiation, along with fierce stellar winds, ripped electrons off the surrounding hydrogen atoms in a process called reionization. The cosmic fog, which had cleared once before, was now being burned away for good by the intense light of these stellar behemoths. This period is known as the epoch of reionization. The universe was being transformed from a cold, dark, and neutral place into the hot, ionized, and transparent cosmos we know today. The universe was waking up one star at a time. The dawn had finally broken. These first stars were cosmic trailblazers. They were the pioneers that lit up the darkness. But their importance goes beyond just producing light. Inside their fiery cores, they were forging heavier elements for the first time. Through nuclear fusion, they created carbon, oxygen, nitrogen, the very elements necessary for life. When these massive stars reached the end of their short lives, they didn't just fade away. They exploded in spectacular supernovae, scattering these newly forged elements far and wide across space. They seeded the surrounding gas clouds with the raw materials for the next generation of stars, and eventually, for planets and people. The birth of the first stars was just the beginning. These stars didn't form in isolation. They were born in clusters, deep within the dense cores of the dark matter halos. Each of these clusters, a collection of stars, gas, and dark matter, was a galaxy in the making. We call these early, small-scale structures protogalaxies. They were the cosmic building blocks, the humble Lego pieces from which the grand galactic empires would be constructed. They were much smaller and messier than the majestic galaxies we see today. Clumpy, irregular, and fiercely bright with the light of young, massive stars. These proto-galaxies were scattered throughout the cosmic web, like tiny islands of light in a vast ocean of darkness. But they weren't destined to remain small and separate forever. Gravity, the ever-present sculptor, was still at work. The same force that pulled gas together to form the first stars was now pulling the proto-galaxies toward each other. The universe was a dynamic, bustling place. These small, infant galaxies were on the move, drawn by the gravitational pull of their neighbors and the larger dark matter structures they inhabited. The era of galactic construction had begun. Imagine a cosmic construction site. Over hundreds of millions of years, these proto-galaxies began to merge. When two proto-galaxies drew close, their mutual gravity would pull them into a dramatic dance. They would swirl around each other, distorting their shapes until they eventually collided and combined into a single, larger entity. Each merger added more stars, more gas, and more dark matter to the growing system. It was a process of hierarchical assembly, small things coming together to make bigger things. This is the fundamental way that large galaxies are built. This process of merging and accretion continued for billions of years. Proto-galaxies combined to form small galaxies. Small galaxies merged to form medium-sized galaxies. And medium-sized galaxies collided to create the giants we see in the universe today, like our own Milky Way and its neighbor Andromeda. This cosmic story is one of assembly, of small beginnings leading to grand structures. Every large galaxy you see in the night sky is a testament to this long and violent history of mergers. It's a cosmic family tree, with countless smaller ancestors coming together to form the present-day galactic titans. The merging of galaxies is, honestly, one of the most spectacular events in the cosmos. It's like a slow-motion collision that can take hundreds of millions of years to unfold. When two galaxies approach each other, their immense gravitational fields start to interact long before they actually touch. They pull and stretch each other, creating these long, wispy tails of stars and gas that extend for thousands of light years. These are called tidal tails, ghostly streamers that really trace the history of the gravitational encounter. The galaxies themselves become distorted, their beautiful, orderly structures twisted into chaotic, irregular shapes. It's a violent and beautiful cosmic dance. Now, you might think that when two galaxies collide, their stars would crash into each other. But actually, space is mostly empty space. The distances between individual stars are so vast that direct stellar collisions are incredibly rare. It's kind of like two swarms of bees flying through each other. The individual bees almost never touch. Instead, it's the gas clouds within the galaxies that collide head-on. These collisions are monumental. They compress the gas, triggering a massive burst of star formation. The merging galaxies light up with the brilliant blue light of millions of newborn stars, becoming what astronomers call a starburst galaxy. This burst of star formation is a key part of galactic evolution. It uses up a significant portion of the available gas reservoir in a relatively short amount of time. The merger process also scrambles the orbits of the existing stars. In a spiral galaxy, stars move in orderly circular paths within a flat disk. But during a major merger, the powerful gravitational forces throw these stars onto new, random, elliptical orbits. The neat, organized structure of the original galaxies is completely disrupted and rearranged. The collision acts like a cosmic blender, mixing everything up. This process of merging and colliding is fundamental to how galaxies grow and change over time. It's not just about getting bigger, it's about transforming their very nature. A major merger can completely change a galaxy's shape, its rate of star formation, and even the behavior of its central black hole. Our own Milky Way is no stranger to this process. We can see evidence of it having consumed smaller dwarf galaxies in the past, and well, it is currently on a collision course with the Andromeda Galaxy. In about 4.5 billion years, our two galaxies will begin their own grand cosmic dance, eventually merging to form a new giant galaxy. As galaxies grow through mergers and accretion, they tend to settle into one of two main shapes, spiral or elliptical. These two types of galaxies tell different stories about their pasts. Spiral galaxies, like our own Milky Way, are majestic, spinning disks of stars, gas, and dust. They have beautiful spiral arms, which are regions of active star formation, glowing with the light of young, hot blue stars. These arms are density waves, like cosmic traffic jams, where gas clouds get compressed and trigger the birth of new stars. The disk itself is a place of orderly, rotational motion. The formation of a spiral galaxy requires a relatively gentle history. It starts with a large rotating cloud of gas in a dark matter halo. As this gas cools and collapses under its own gravity, its rotation speed increases, just like a figure skater pulling in their arms to spin faster. This principle, called the conservation of angular momentum, causes the gas to flatten into a thin, spinning disk. This disk is where subsequent generations of stars will form, inheriting the orderly, circular motion of the gas. To maintain this delicate structure, a spiral galaxy can't have undergone a recent major merger with another large galaxy. Elliptical galaxies, on the other hand, are very different. They are smooth, featureless, and generally spheroidal or egg-shaped. Unlike spirals, they have very little gas and dust, and almost no ongoing star formation. Their light comes from older, redder stars that move on random, crisscrossing orbits, like a swarm of bees buzzing inside a jar. There's no organized disk-like rotation. This chaotic motion is a telltale sign of a violent past. Elliptical galaxies are thought to be the end product of major mergers between large galaxies, especially two or more spiral galaxies. When two spiral galaxies collide, their disks are destroyed. The gravitational chaos of the merger flings the stars onto random orbits, creating the puffy, spheroidal shape of an elliptical galaxy. The intense burst of star formation during the merger uses up most of the available gas, and the rest is often heated up and blown out of the galaxy. With its gas supply depleted, the newly formed elliptical galaxy can no longer create new stars. It becomes what astronomers call a red and dead galaxy, slowly fading as its old red stars age. The shape of a galaxy, therefore, is a fossil record of its history. Galaxies are not static objects. They are dynamic, living ecosystems. At their heart is the continuous cycle of star formation, the process of birth, life, and death that shapes the galaxy's evolution. In spiral galaxies, this process is most visible in the beautiful glowing arms. These arms are rich with vast clouds of cold molecular gas and dust, the raw materials for making stars. These clouds, sometimes called stellar nurseries, are where gravity can overcome the gas pressure and begin to pull material together into dense clumps. These clumps continue to contract and heat up until they ignite as new stars. The life of a star is determined by its mass. Low-mass stars like our Sun are frugal with their fuel. They burn hydrogen slowly and steadily for billions of years. They live long, stable lives before eventually puffing off their outer layers to form a beautiful planetary nebula, leaving behind a dense, cooling core called a white dwarf. High-mass stars, however, live fast and die young. They are the rock stars of the universe. They burn through their fuel at a furious rate, shining brilliantly for only a few million years. Their lives end in the most spectacular explosions the universe has to offer. Supernovae. These supernova explosions are incredibly important for galactic evolution. They are the universe's great recyclers. The explosion blasts the outer layers of the star out into space at incredible speeds. This material includes not only the hydrogen and helium from the star's original composition, but also all the heavier elements that were forged in its core during its lifetime. Elements like carbon, oxygen, silicon, and iron. These heavy elements, which astronomers call metals, are scattered far and wide, enriching the interstellar gas clouds from which they came. This enrichment is crucial. The very first stars were made of only hydrogen and helium, but the next generation of stars formed from gas that had been seeded with these heavier elements. Our Sun is a third-generation star, rich in metals forged in the hearts of long-dead massive stars. These metals are what allow for the formation of rocky planets like Earth. And of course, they are the building blocks of life itself. The carbon in your cells, the oxygen you breathe, the calcium in your bones. Every atom in your body heavier than hydrogen was created inside a star. We are, quite literally, made of stardust. At the center of nearly every large galaxy, including our own Milky Way, lurks a monster, a supermassive black hole. These are not the ordinary black holes formed from the collapse of a single star. These are behemoths, with masses ranging from millions to billions of times the mass of our Sun, all crushed into a region smaller than our solar system. Their gravity is so immense that nothing, not even light, can escape their grasp. How these giants formed is still one of the great mysteries of cosmology, but we know they play a crucial role in the life of their host galaxy. These supermassive black holes didn't just appear out of nowhere. They likely started small in the early universe, perhaps from the collapse of the very first massive stars, or from the direct collapse of huge gas clouds. Then they grew over cosmic time. As protogalaxies merged, their central black holes would also merge, creating a bigger black hole. They also grow by feeding on the gas, dust, and unfortunate stars that wander too close. As this material spirals into the black hole, it forms a swirling, superheated accretion disk. This disk can shine more brightly than all the stars in the galaxy combined, creating a phenomenon known as an active galactic nucleus, or a quasar. This process of feeding, known as accretion, has a profound impact on the entire galaxy. As the accretion disk blazes with energy, it can launch powerful jets of particles and radiation that travel at nearly the speed of light. These jets can plow through the galaxy, heating up the surrounding gas and blowing it out of the galactic center. This process acts like a feedback mechanism. By clearing out the gas, the black hole effectively shuts down star formation in the central regions of the galaxy. It's a form of self-regulation, preventing the galaxy from growing too large or forming stars too quickly. The black hole, therefore, is not just a passive object sitting at the center. It's an active participant in the galaxy's evolution. The relationship is symbiotic. The galaxy provides the fuel, the gas and stars, that allows the black hole to grow. In return, the black hole's energy output regulates the galaxy's growth and star formation activity. This delicate balance helps explain why we see a tight correlation between the mass of a galaxy's central bulge and the mass of its supermassive black hole. The monster at the heart of the galaxy is not just a destroyer, it is also a co-creator, intimately linked to the life story of its cosmic home. From the simplest beginnings, a hot, uniform soup of particles, the universe has constructed a breathtakingly complex and beautiful tapestry. The story of galaxy formation is our story. It's the story of how gravity, the patient architect, took the primordial elements and, with the help of invisible dark matter, sculpted them into the grand structures we see today. It's a story of cosmic construction, from the first tiny ripples in space-time to the majestic spiral and elliptical galaxies that populate the cosmic web. It's an epic of creation, played out over 13.8 billion years. We've learned that galaxies are not islands, but dynamic, evolving systems. They are built through a violent and beautiful history of mergers and collisions. They are alive with the constant cycle of stellar birth and death, a process that forges the very elements that make us possible. We've discovered that at their very hearts lie monsters of gravity, supermassive black holes. that regulate their growth in a delicate cosmic dance. Every discovery reveals another layer of the intricate connection between the largest and smallest scales in the universe, from the quantum fluctuations of the Big Bang to the galactic superclusters of today. Our own galaxy, the Milky Way, is just one of hundreds of billions of galaxies in the observable universe. And our Sun is just one of hundreds of billions of stars in the Milky Way. When we look up at the night sky, we are not just seeing distant points of light. We are looking back in time. We are seeing the fossil record of cosmic evolution. We are witnessing the grand narrative of how the universe became a home for stars, for planets, and for us. It connects us directly to the beginning of everything. The quest to understand how galaxies form is far from over. With every new telescope, like the James Webb Space Telescope, we peer deeper into the cosmic dawn, capturing images of the very first galaxies beginning to form. We are constantly refining our models and challenging our assumptions. The universe is still full of mysteries. The nature of dark matter, the origin of supermassive black holes, the ultimate fate of galaxies. But that is the beauty of science. It is a journey, not a destination. It is an ongoing, unfolding story. And we are privileged to be living in a time when we can read its pages.